the homework, the so-called homework number 1 of the last year. And the homework number 1 of the last year was on MIMO. Okay? So I'm not discussing how to set up the MIMO model, because my plan is as soon as we do the first lab together, we discuss about the homework of the last year. So in this way, you know, you can see and we can discuss practically on the MIMO. Today we need to make a step forward and we need to review something. Okay. So first of all, I consider this one as a review. So what I say is that, you know, perhaps all the subjects we are going to discuss today are well known. Perhaps, you know, it's pretty well known, but I mean, there are some uncertainty. Perhaps it's not known, but you need to consolidate a little bit, so it doesn't matter. I mean, in a way or another, by the end of the semester, all the concepts that I'm going to describe now today should be consolidated. So you have 3 months to consolidate, okay? So let's start. So first of all, you know, what is a random variable? So a random variable is a variable that is random, okay? So it's not deterministic. Huh? So I cannot classify that variable with a specific property where, you know, it's a fixed value. So it's random, and then, you know, this random variable is classified by the corresponding probability. And for instance, you know, I can indicate the probability density function Px, or here, Px of x, okay? So this one is a probability density function for the random variable x, okay? So what does it mean? It means the following, that if I want to know what is the probability that the random variable x stays between 2 values, a and b, then I just take the probability density function that I indicate as a PDF. So for me, when I say PDF, means a probability density function. Since we would say many times PDF, so, you know, I mean, I try to remember to say probability density function, but, you know, it's quite common to say this. It's Gaussian PDF, it's uniform PDF, and so on. Okay. So now, if the probability density function is given by a certain function, then the integral of that probability density function between the interval a and b gives me the corresponding probability. Okay? So it gives me the probability that the random value stays within the value a and the value b. Now, the specific random variable that I'm considering is indicated by the subscript. Now, but you know, I mean, loosely speaking, Px is a function. So that one is a function. So if I ask myself, what is the integral of the function, which is Px, what is the integral of the function between a and b? That is as a certain value. This value is the probability. Now, it makes no sense that the probability is negative. So for this reason, you know, the probability density function is strictly positive or equal to 0. So it's always larger or equal to 0. Now, second, since I can take a going to minus infinite and b going to plus infinite, then I'm saying this way, what do I mean? I mean that, you know, if the extreme are going from minus infinite to plus infinite, I include any value of the random variable x. So the probability that the random variable that exists, which means I consider that there is this random variable. Okay? So the probability that the random variable stays between minus and plus infinite is 1. Okay? Because that random variable exists. So that means that, you know, in this case, for a going to minus infinite, and b plus infinite, so in this case, you know, the integral of px of alpha dx, d alpha, is equal to 1. Okay, so the area, the overall area, is normalized to 1. Now, we can define another property. Another property is not the probability density function, but is the integral. Okay? The cumulative density function, CDF. Okay? Now the cumulative density function is the probability that the random variable is lower than a certain value. So what is the probability that the random variable is lower than 10? Now, you know, this can be obtained by taking the probability density function integrated by minus infinity to specific value, okay, which is x0. So, since the probability density function is as the area that is normalized to 1, this is lower or equal 1, okay? The complementary one is 1 minus that, which is the probability. What is the probability that the random variable is larger than x0? Then this is 1 minus the probability that it is smaller than x0. Okay? And this is just a complementary. So let's make another step forward. Now, what about if these random variables is not continuous but is discrete? I don't know, if you consider like the bit that you transmit. If you have a bit, the bits are 0 and 1, right? Okay, and you know, so that one is a discrete set. So 0 and 1 is a discrete set of random variables. If you take, I don't know, if you toss what else? Random variable. I mean, if you have a card, playing card, okay, you have 52 playing card. So every card you can select randomly one card, and the probability of choosing randomly one card is 1 over 52. This is common sense, right? So, but you know, the number of cards are 52, so it's limited set. In this case, that one is totally different from the previous case, where the random value is continuous. It's going from minus infinity to plus infinity, and it can take any value. So the probability mass function, okay, PMF, says that I have a discrete countable set. Okay? Countable means, you know, I can count it. So I cannot count the real numbers. So, you know, because there is no way to count. But, you know, if I take a countable set, like integer, 1, 2, 3, 4. So any number that goes between 1 to 300. Okay, this can be countable. Now, in this case, I can define the probability pk, and pk is the probability that the variable is equal to xk. So, this pk, since this pk is representing the probability associated to the value xk, then the sum, in that case, of those probabilities should be 1. Okay? So if I take, you know, 52 cards, the probability that I choose, I don't know, the one of the king or whatever, okay, it has a certain value. And the probability that I can choose each one sum to 1. Because, I mean, when I choose, I get surely one of those 52. Now, if I want to put together the representation on the previous case, which is continuous, and the representation of the second case, which is discrete, what I need to do, I need to define the delta function. So the delta function has a property that has a unit area, right? Area, okay? So since the delta function has a unit area, then I can represent the probability mass function can be represented in terms of probability density function, okay? This is the density. So this is obtained, you know, by a set of delta, as indicated here, okay? So which means that if I represent this space, I have a set of delta. And, you know, the area of this delta is representing the corresponding probability, the area, okay? The area. Now, okay, good. By the way, if we have to do with some classification problem, okay, now the probability is associated to each class and each element inside the class. So this, I mean, what I'm saying is that, you know, the probability mass function and the countable set is not necessarily the numbers. So I can say that, I don't know, I have a name of the people, Mario or Rossi, I mean, I don't know, whatever is the name, okay? And so if I say, what is the probability that if I pick up one person and I randomly pick up one person, and this person is going to be called Mario Rossi, okay? Mario Rossi for the foreigners are very common name. It's a very common name, okay? Mario is common and Rossi is slightly less common now, but you know, so Rossi, you know, is, I think it's more, if you count how many last name Rossi is existing in Italy, I think it's one of the top, okay? So, you know, these are Rossi, if I choose one randomly, then what is the probability? And this is described by that. But you know, Rossi is a name. So the class that I am describing is now a class of names, which is different from number, okay? So since I told you, I added a new part in the course, okay? And the new part in the course is on the pattern recognition part, okay? Pattern recognition and classification and similar topics. Okay. Now, let's move forward. So that means that, you know, the classes are not just numbers. It can be, you know, countable classes represented by names, I don't know, by whatever. Now, we have another property. We can calculate the expected value. Now, the expected value, okay, is a function of the corresponding probability density function. So the expected value is the integral. Now, if I indicate the integral, as in this case, you know, the integral goes between minus infinity plus. Okay? Similarly, as I indicated the sum. If I say the sum, it means sum of. Okay. So now this means that this one is you know, is the integral of g alpha px of alpha and d alpha. The reason why I'm not putting g of x, p of x, and dx is just to remind mentally that this one is a function of x, that one is a function of x, and this x here, the x which is in the subscript, is reminding you, is recalling you what is the random variable. Now, so this expectation can be also written in this way, which means with e, and this one is the expectation of gx. Okay? So if I write this way, it means that I'm taking the expectation with respect to the random variable x. I can also write, and in some cases, I prefer that way. Now, the reason why I indicated expectation with respect to x of gx is the following, because sometimes we have multiple random variables and we need to decide which we calculate the expectation first. Okay? And so, for this reason, imagine g depends on x, y, z, blah, blah, Giovanni, blah, blah, and so on. And then I say, okay, I calculate the expectation with respect to x only. Okay? Now, you might ask me, and what do I make it with Giovanni, Francesco, Maria? Okay, depends. We'll see. So anyway, this is the expectation. Now, I can calculate as a specific g of x, as a specific transformation, the powers. So if I calculate as a g of x, x to the power k, that one is called the moment. So when I say the kth moment, as in this case, so the kth moment is the integral of alpha to the power of k, probability density function, okay, in the alpha. So this is the kth moment. Now, the central moment, okay, which is even more specific, the central moment is the moment about the mean. So what does it mean? It means, by definition, it's defined this way. The central moment, mu k, is the expectation with respect to x of x minus expectation of x. Because that expectation of x is called mean. So the mean, which is it is not indicated here, okay? which is, you know, is the following, and it is the expectation of x, okay? Which is equal, according to the formula, is the integral of x probability of x in the x, or alpha in the alpha, okay? So, now, you know, so the central moment, let me highlight the central moment, okay? The kth central moment is just the same as here, except that I have x minus this value, and this value is the expectation, is the mean, okay? So, if I consider this one, okay, this has a property, because for instance, mu1 is x minus mu x to the power of 1 is the mean, okay? And that one is equal to 0. Mu2 is x minus the mean to the power of 2, and this is called the variance. And then we have more. Third power, fourth power, so we have a third central moment, fourth central moment, and so on. Now, the second part, additional, okay? I can define the Fourier transform, since the probability density function is a function, I can calculate it through the Fourier transform function, right? Okay, so since I can calculate the Fourier transform, then I give a name to that. So look at this formula from the right to the left. So from right to the left, this is the Fourier transform. So if you like, you know, I can indicate as Fourier transform of Px of x. Okay? So this is a Fourier transform of Px, but you know, if I write it, the Fourier transform, then this Fourier transform is simply taking this one, this play the role of g of x. Okay? So this g of x is a transformation. So that one, you know, is indicated here. Okay? So this one, I told you, read from the right to the left. This one is called a characteristic function. Okay? Now, this characteristic function, the reason why the people define the characteristic function are the following. Number one, in some cases, it's much easier to compute the moments by the characteristic function. Okay, so if you have everything in a transform domain, if it is easy, you keep it in the transform domain and you compute the moments there. Second reason is which is indicated here. So first motivation here. It's easy to compute the moment. Okay? And this property comes from the property of the Fourier transform. Second, it is, you know, second reason, I'm indicating here. The second reason is the following. Assume that I have a random variable, which is the sum of 3 or many random variables. So a random variable is the sum of x1 plus x2 plus x3 plus x4 plus blah blah blah. Okay? We know from the theory that the probability density function of this random variable is equal to the convolution of those individual probability density functions, and then, you know, the convolution of this one, okay? So which I indicate here just to stress the notation, but never mind. Okay? And this is true when the random variables are statistically independent. We will see in a minute. Okay? But you know, it's convenient that, and we know that anytime I work in the Fourier domain, convolution becomes a product. So if I need to calculate these convolutions, which in some cases feel complicated, but it might be easier, for instance, to calculate the convolution as a product of the Fourier transform, which is the product of the characteristic function. Okay? The third reason, which I know list here, the third reason is that there are some probability density functions that are very difficult to express in the regular domain as a probability density function, but they are more easy to be expressed in transform domain as a characteristic function. Okay, there are some special classes. Probably you don't see it, okay, in your life. You will see it, okay, but you don't see it in your life. And so for this reason, you know, you never met it. But I mean, remember these words, okay? Now, I said, I mean, up to now I said I have one random variables or one random variables as obtained by summing, okay? Now, let's consider more than one random variables. Let's assume that I have two random variables. So, I don't know, I have a voltage in the top and voltage in the lower part of the nerve, okay? So, now, think about if the amplitude of the signal here in the top of the nerve is a random variable, and if the amplitude of the signal is the lower part of the nerve is a random variable, then, you know, if when I change it here, that one doesn't change, that means that they are not related to one another, right? But if when I change here, start to change there, then, you know, they are related. So we need to introduce the notion of independence, correlation, or uncorrelation. So uncorrelation and independence means if I take two random variables, that they have nothing to do with each other. And the two random variables are correlated, means that you know, if something happens in one random variable, it's changing the other. Okay? Now let's try to be more rigorous on that. First of all, it's you know, we need to define the probability density function for both random variables. So that now the function depends on two variables, okay, which is x and y, for instance. So we have a joint PDF, which is a function of two or more variables, okay. During the semester, we will work with n arbitrary random variables. It's not just two. But you know, since we were working with arbitrary n, this n can be 100, can be 1000. Okay? So, since this n is very large, then you know we need to learn what is the inner meaning of some of the properties that we work with two random variables. Now, first of all, the property, you know, is positive, okay? And now the integral on two dimensions, which is called the volume. So the volume of the joint probability density function is normalized to 1. Okay, this, you know, is kind of obvious, but I mean, what do I expect? Now let's look at, let's look at a little bit. Now what I do is surprising you. I mean, sometimes it's surprising. Okay, so let's try not to surprise, but I mean, let's try to express something to you. So the probability, what they call it, p, x, and y. So p, x, y is a function. Okay, it's a function of the two random variables x and y. Okay. So that means that, you know, I can represent where this is x, this is y, and I don't know, I have this behavior. Okay, so it's like a sausage being commanded. Okay? So I know that the volume of this ball, okay, is 1. Volume. 1D is area, now is volume. Okay? The volume is 1. Now I'm defining one quantity. The first quantity I'm defining is the following. I want to define the so-called, you know, projection. What is the projection? The projection means that, remember, these are two random variables, huh? Okay. The projection means that assume that I take one x. And what I do is, when I take this x, and I cut it, this is what I get by cutting. Let me see if I can make it so that you get a nice picture. Okay. So that means that I have a certain x naught. So if I choose a certain x naught and I cut it, okay. Now that one, is a probability density function that depends on what? On y, because x is fixed, right? So if I choose x, what's happening? If I choose x, that means that x is no more random. So if I take x, so if I say that x has a certain value, x is no more random. Okay, now, very simple example. Assume that you want to know two parameters. One is, what is the time in my watch? And the second random variable is where I am now, in the room, right? Okay. Assume that you are outside and you don't know where I am. So you can make a guess. You can say, I don't know, I'm approximately here. And here, but I might be here with more probability and here with less probability. And perhaps I'm not jumping on the table. So the probability that I am on the table is very small. So that means that, I have a kind of sausage-like probability density function, which is related to my position. Okay? Probability density functions are not magic, are describing the world. Okay? So mathematically, it seems magic, but I'm describing the world. They are tools. Now, so you don't know where I am. Okay? Before opening the door. Now, you open the door. By the way, remember, the two random variables are my watch and my position. Okay? So you might say where I am. What time is that? There are two variables that they have nothing to do with each other. Let's forget them for now. Now, when you open the door, you watch me, you see where I am. I'm here. So since I'm here, for you before opening the door, the time and position were two random variables. Actually, position is two-dimensional, but forget for a minute, okay? So, before opening the door, you had two random variables, position and time in the watch. But once you open the door, the position is fixed. And what remains random is the time in the watch. Okay? This is exactly what's happening. If I take the two-dimensional probability density function and I fix one value, what I do is that that value is no more random. And so since that value is no more random, then I need to write it. So how can I write it? Now I can write it this way. I can say that my probability density function for x equal x naught, and then depends on y. Would you do this way? Yes or no? Too simple, right? Yes. There is a trap, okay? But about what I'm saying, it's perfect. There is nothing wrong on the reason. But there is one big mistake that I'm making. What is the probability density function? Now, this, in principle, should be a probability density function of y. Because y remains uncertain. X is given. My position, is given. But, the watch remains uncertain. Now, is it this one that I choose by cutting along x equal x naught, a probability density function? Is it this one a probability density function of y? Is it truly a probability density function? Now let's go. It is positive? Yeah, it's positive. The first one was positive, and you know, this is positive, right? Is it normalized to 1? No. Okay? So, what they do is the following, you know. I mean, what I need to do is that I need to divide this one by the integral of p x y. Okay? So, in the okay. So, if I do this way, what's happening is that now this probability density function is really a probability density function. So, what I need to do is to take this area and normalize the area after slicing. You see slicing because I cut it, okay? After slicing, I need to normalize the area after slicing to 1. Okay? Now, if I do this way, that one becomes a probability density function. So this one is the probability density function of what? Of y. But you know, x is deterministic. So how do I write x is deterministic?
Given.
Is x equal x naught. Okay? And I write this one. Sorry, the opposite, yx. Okay? Is it clear what is the conditioning? This is called conditional PDF. Okay? So when I have a conditional PDF, means that I'm fixing one of the random variables to some value that might be arbitrary. Okay? Is it clear? Simple? You will see how many times you will make a mistake on that. Huh? Okay. Now, so step number 1. And by the way, you know, we say, okay, it's easy, but I studied a different formula. The formula is not the same, right? You studied bias formula, right? So you remember that, okay? And that this formula has nothing to do with that. Okay? We will see that it's the same. A little bit loose, but it's the same. Now let's continue with this reasoning, okay? About the formula. I mean, we have time in the life to learn about formula. So, but the concept, you know, if you don't learn here the concept, perhaps in the like industry or whatever, they don't explain the concept because they have no advantage to explain your concept, because as soon as you explain concept to someone else, that someone else becomes an enemy, becomes a competitor. Okay. So that's the beauty of the university. You are never a competitor or anyone until you graduate. The day after graduation, you are one competitor to another. Okay? So that's that's now. Let's revisit this concept and let's make something else. Suppose now that I do a similar one, but I calculate the area for a given x. So let me sketch differently. Okay? Let's take the same sausage. I mean, by the way, let me grab it. Copy. Beautiful. I like this. Okay, so let's take the same example. Huh? Now, you know, I don't take x naught, I take any arbitrary value. Okay. Now let me cancel the other comment because we are slightly different. Okay, let's take 0. Okay. Now I do a different operation. I don't slice, I sum. So what I do is I fix a certain value and then I sum all the entry along this value. So I sum here, sum, blah, 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 okay? So I look at the map view And so what I'm doing, I have the sausage, the shape, which is the support. Technically, this is called support. You know what is support? Support is the area where the function is different from 0. Okay? So this one is support, which is means looking from the top. So what I do is I take a certain value x0, okay, and what I do, I sum it. I sum it. Now, let's write what does it mean. So that means that I take P, the two-dimensional one, I fix x we call x0. You know, I take y as a variable that is integrating variable, and then I integrate over y, dy. Okay? So I'm integrating, fixing x, integrate over y, right? Okay, now this one is projection. So this is the part of the course that we replaced with the machine learning part this year. But you know, this is called projection. So when I have a two-dimensional function and I integrate in one dimension, it's called projection. In a statistical sense, this is called marginalization. And before giving the formula, what is the meaning? The meaning is the following. It means that I take one of the random variables and I integrate with all the possible state of the second random variable. So that means fixing one random variable and integrating all the states. When I integrate, I sum every value with a corresponding probability. Really, I sum every value y for the corresponding probability. I'm summing. So this one now becomes, depends only on x. Because of over y, you know, I remove all the dependency. Okay? So this one becomes the marginal probability density function, okay, of x only, because it depends on x, not on y. So now you know, now that you, that you have this feeling about that. Now let's see, you know, the formal description. Okay, this is the intuitive, so that you know the intuitive remains. Okay, the aseptic formula, you know, perhaps you might forget. Now let's go to the part. So marginalization, also the marginal PDF, which means I have a probability density function depending on two random variables, and I want to remove one random variable. Now this kind of operation, marginalization, is carried out every time that you don't know, for instance, the specific value of the other variable. For instance, you know, assume that you have like here px y, and you cannot establish how is y. What is y? Since you cannot establish, you know y only statistically, so you prefer to average it out, which means summing on all the possible states, all the possible states over the unknown variable y, and get the dependency on the variable that you have under control. So this is the marginalization. So if I have a two-dimensional or a joint probability density function of two variables, if I integrate with respect to one, I get the marginalization. So I get the one-dimensional probability density function for the other variable. And similarly, you know, if I interchange the two two axes with respect to x and with respect to y. Again, formally, okay. 1 minute here. Look at that. Now, if I want to calculate the marginal probability density function, so that what I do, if I want to calculate the conditional probability density function with respect to y, sorry, I swapped x and y here, okay? So if I want to calculate the probability density function conditional with respect to y equals y0, what I need to do, I need to cut it, y0, and then to normalize. But you know, this formula is a bias formula. So you recognize the first one. But you know, this one, by the marginalization rule, is exactly that. And this one is the normalization factor that I just wrote. Okay? So the bias formula is nothing else than what we intuitively discussed. So this one, you know, is normalization. Now, specifically now, two random variables are considered statistically independent. Now, statistically independent means they have totally nothing to do with each other. They have no reason to be put together. Okay? No reason for that. Like, what is my position and what is the time that I have in my watch? Nothing to do. Because if I'm here, there, the time is the same, right? Or the error with respect to the absolute time, whatever is the absolute, okay? So these are two statistical independent. Analytically means that the joint probability density function is obtained by the product of the marginal probability density function, which is Px and Py. That's, you know, by the formulas and by the constant. Let's move forward. I made a couple of examples. How to compute the conditional, the mean of the conditional mean. So what is the conditional mean? Now the conditional mean means that I want to calculate the mean when one of the variables is fixed. Okay? Now, by the way, this random variable to be fixed can be due to the fact that you are measuring. Remember, before opening the door, the position, my position, according to what is outside, is a random variable that has a distribution, which is a probabilistic distribution, can be everywhere, here, okay? With, let me say, very small probability that I stay in the table, okay, jumping on the table, which is not, I mean, if I say probability 0, means that it's impossible. 0 means 0, okay? But if the probability that I stay in the table is 10 to the minus a, means that it's unlikely but not impossible. Okay? Now with this trick, you know, it's I mean, if you with the common people, impossible and unlikely is the same. But for you it should be different. Okay? So impossible means it's probability 0. Okay? So what is the probability that, you know, if I am there and after 1 second I will be outside of the window passing through the wall? Impossible, right? Because, you know, nobody has ever observed anyone that is passing through the wall except what was that magician? Harry Potter, right? Okay. So except the movie, huh? But you know, if you go beyond that, it's impossible, right? So the probability is 0. But if I consider the probability that perhaps I sit on the table, I don't know, perhaps, I don't know, during the semester I might sit at the table. I mean, during my life, let me see if I ever have been standing over the desk here. Okay, I don't remember actually. But yeah, so anyway, well, let's make, you know, you take the life, you take, oh, as a student for sure. When I was student for sure, okay. But so I was not a very disciplined student. But you know, I mean, after that, when I took this role, then I'm not standing here, okay. So anyway, this is the difference between possible and unlikely, okay. There was for foreigners, okay. There was a trial. Okay, the court trial with a court, because there was an earthquake in Italy, and they asked if the earthquake was I mean, was to be happen or to happen or not. Okay. So they asked these experts, huh? And so what did the experts can say? They say, for us, you know, it's perhaps is with unlucky that this happens in the next few hours, okay? And it happened. And so the judge, I mean, says, you said that it's impossible to happen. No, we say unlucky. So if you listen, if you read what they wrote in a technical, scientific way. They say it's unlikely that it's going to happen in the next few hours because we never observed that and this and that. But it happened. But they didn't say it's impossible. So since the word of the scientist went through the politicians say, they say impossible. No, we say unlucky, you see? So the common sense is that unlucky means impossible, okay? So now you can explain your friend at this time, okay? It is not impossible. I mean, impossible is something that is really, really, with the probability zero. It's not zero, close to zero. It's zero, mathematical zero, okay? So anyway, let's go to the point. So I can calculate the conditional mean. Now we know conditional means is that one variable that was random now is fixed, okay? So which means y is equal to y0. So I can calculate the conditional mean. Now look at that. Look at it for 1 second. What does it mean? Now this one means the following. Yeah. So I'm making the reasoning here. So I have my two-dimensional. Okay. I have my two-dimensional. I'm cutting over y's. I'm cutting here. I'm cutting over y0, and then I'm reading it, not just reading the formula. Okay, I'm cutting over y0, and then I compute the barycenter for that. Okay, which is the mean? The mean is here. The mean is such that this area should be equal to the other. So that one is this value, okay, which depends on x. This value is the expected value of x when y is equal to y0. Huh? Okay. So if someone is asking you, someone could be myself, but someone else, okay? If someone is asking you, can you read the formula? Never read the formula integral of alpha p x given alpha given y of alpha given y equal y0 in the alpha. Okay, because this is what can read anyone, which knows nothing on that. So you can read the formula, which means I need to calculate the mean of the conditional PDF, which is calculated by the conditional PDF, which is conditional with respect to one value of y0. Read the formula. Learn how to read the formula. I will insist a lot on that. This gives a difference between a machine, a computer. If you ask a computer to read the formula, and the computer might talk, it reads integral of alpha blah blah. But you are not a computer. Computer is the stupid part. So try to be smart. Try to read. Learn how to read the formula. Every formula has meaning. It has a hidden concept on that. Read it. I will make a lot of effort on that to help you to read. Now, okay, so we computed the expected mean. You see, I highlighted the expected mean is computed with respect to y, to x, okay? Because y is not random. Now, since I fixed y 0, okay, then I computed this random variable, then I might compute something else. So I might say, wait a minute, y was not a random variable. Y was not a deterministic variable. Y was a random variable. So I just temporarily fixed. But then I consider the randomness of y. So let's see. So if I needed to compute now the expectation of, with respect to y, of the argument, means inside the argument, y is deterministic. But then I say, okay, I made a mistake. Y is not deterministic, it's random. Then you know I can expect, so compute the expectation with respect to y. So in formula, okay, this means that I take the inner part, and in this inner part, y equal y0, and is temporarily deterministic. Okay, inside here. But then I give it back the random property to y, and then I compute the expectation with respect to y. Now, this method to compute is a very convenient way to calculate the mean, okay, the mean with respect to x and y of whatever function. Now, once again, let's generalize the concept. So the expectation of any function. So suppose that I have now a function of x and y, and I want to calculate the expectation with respect to both variables. Now, what I can do is the following. I can calculate first the expectation with respect to x when y is fixed. Then, outside, I compute the expectation of y. X does not exist anymore because I computed the expectation of respect to x. Okay, so in this way is a very convenient way to compute the expectation of joint two or more random probability by slicing, this calculus into fixing one variable and then releasing the deterministic part of that variable. And of course, this commutes with the other. Okay. Another example, even more easy. Assume that I have x of k. X of k is a set of random variables. And these random variables are independent and identically distributed. Okay? So, these x are independent. Independent means that one is statistically independent from another. So they are statistically independent one another. Okay? And identically distributed. Okay, what does it mean? It means that the probability density function of x1 is equal to the probability density function of x2 is equal to the probability density function of x3 and so on. They are all with the same probability density function. Now this condition is indicated commonly as IID. Okay? IID is, for instance, we will discuss on that, is a white noise. The white noise, all the samples are independent and statistically independent and identically distributed because they are distributed in the same way. We will discuss on that. Now let's assume that I want to calculate the sum of n IID, so independent and identically distributed random variable, where n is unknown. So the number of samples is unknown. So I don't know how many samples I'm computing. So I make the sum of an unknown number of samples, and I want to calculate z. Okay? So I don't know, it means that if I want to calculate the height of u, okay? So the sum of your height, but you know, the number of u is unknown. And so it's a random variable. So we have two random variables. One is n, and the other is xk. Okay? So how can I compute it? Now the way to compute is that I have a function, g, and the function g depends on n random variables plus n, which is how many. Okay? So how many is a random variable itself. So how do I compute? So what I need to compute, I need to compute the expectation with respect to all the random variables and n. Okay? So what is the, you know, this sum? Now I decouple the sum in this way. I first, you know, I keep n as fixed, and then I compute this sum. Okay? And so that means that, you know, I'm taking the expectation of x, keeping n fixed. Okay? If you like, you know, say n equal bar. Okay? And then I take the expectation after. So now, since they are independent and identical distributed, it means that the expectation of all these entries are all the same. So that, you know, this means that I have n times that, okay? Which is unknown. And so, you know, this expectation, now the random variables stay here. Okay? And so, this expectation depends only on n. And then you know that's the case. Okay? If you don't do this way, you can never make it. Believe me, you don't make it. So sometimes if you cannot manipulate a formula where you don't know how to calculate these expectations because you have two random variables, you don't know which one to do, fix one and operate with the other. Now, sometimes we have two random variables that are uncorrelated. Uncorrelated is not a powerful property. Uncorrelated happens quite quickly, quite often. Okay? So now suppose that, you know, two random variables are uncorrelated. Now if they are uncorrelated, that means that, you know, the expectation, okay, is equal to 0. Okay? So two random variables are statistically uncorrelated if x and y, yes, the product between x and y is equal to 0. And this comes the correlation function that we will see when we consider the signals and, you know, the spectral properties of the signal. Now, remember, you know, if two random variables are statistically independent, we have that the probability density function joint is the product of the marginals. But you know, this means that if they are statistically independent, they are also uncorrelated. But if two random variables are uncorrelated, they are not necessarily statistically independent. Okay? Except for Gaussians, that we will see in a minute. Now, let's make an exercise. Okay? So a conceptual exercise. Let's consider two random variables that are uniform. Okay? So let me go here in the picture. So I have two random variables that are uniform. So these two random variables that are uniform, okay, here it is. The probability density function is belonging to this area. You see the dashed part, okay? So I have a uniform probability density function. So if it is uniform, you indicate with U. If it is uniform, means that the probability density function is constant. Okay. So if I say that X is uniform between A and B, that means that the probability density function is uniform between A and B. Okay? This is the right. And of course, since the area should be 1, this one is equal to 1 over B minus A. Okay? So this is the case when, you know, two random variables and one random variable is uniform. And I say, when I write X is uniform, means that, you know, it's behaving this way. Now, so let's consider the case where two random variables are uniform, as there, and they are distributed as in a dashed line. So the dashed line there. So which means originally X, as in the picture, okay? So X is uniform between minus A and A. Minus A. Minus A and A. And Y is uniform between minus A and B. Okay? So when I say these two random variables are, let alpha and beta be independent random variables. Okay, that's what it is. Okay, alpha and beta are independent random variables. And you know, alpha is uniform and beta is uniform. This means that these two random variables are, okay, so, you know, if this is alpha, this is beta, and so this is kind of box. Okay. A box like this. Huh? Okay. So rather than writing this way, you know, I prefer to indicate by the support. Okay. Now let's take these two random variables, okay, which are statistically independent. Now what is a statistical independence? Another way. A statistical independent means that, you know, I can compose the 2D function as a product of each individual. Which means that, you know, in matrix we saw as a rank 1. You remember rank 1 is multiply 1 to the other. Okay, so it's stripes. Okay? Anyway. So put a note similar to rank 1. Okay, so that you figure it out. Anyway, so this is the, you know, the 2D. Now, what about if I take this one and rotate the axis? So that means that, you know, I rotate the axis this way. Okay? So if I rotate the axis this way, then means, you know, I call this one this. I need to rotate the axis, okay? So that means that this is X, this is Y, okay? Just one rotating on the other side. And this gives me the picture. I know that if I make a rotation, I have a certain rotation matrix, okay? The rotation matrix makes X is equal to cosine alpha minus sine beta. And Y is equal to sine alpha and cos beta. Okay, this is what comes out. So alpha and beta, you know, are now coupled together. Okay, because I mean, after rotation, alpha and beta, you know, they are no more independent, surely. How do I see it graphically? Because if I just rotate my rectangular, okay, it becomes tilted. And there is no way I can write a function such that their product becomes this shaped behavior. Okay, this one. So I cannot find any product because of the corner. This corner is difficult to make it by product of two functions. So that means that by rotating I lose the independency, the statistical independency. I might find, this is a good exercise, I might find the rotation such that the correlation is zero. But you will see that, that this case is corresponding to a certain angle which is different from zero. So any angle that is different from 0 and 90 degrees makes the distribution to be not independent. So they're dependent. And now similarly, I can calculate, for instance, okay, so in this case, you know, if I rotate, I can calculate the conditional PDF. You remember, conditional PDF means I cut it, okay, which means y is equal to y0, and then you know this area should be 1. Okay? And similarly, if y is equal to y2, I cut it, and this area should be equal to 1. Okay? This is the condition. And also I can calculate the marginal PDF. Marginal, what is marginal? Marginal means, you know, I take and I slice it and I integrate. So it means integrate, blah, blah. Okay? So this is the marginal PDF and the marginal PDF. So if I multiply this by time that, I don't get this one. Okay? I don't get this one. So this is another visual representation of the case that, you know, the independence means that they are separable in two parts. Okay, this is, I gave you already the computation. So what is the rotation such that I can guarantee to be uncorrelated, blah, 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 and so forth. Okay, you can check this out. Now, so far we've seen, you know, arbitrary. Now let's see Gaussians. So what is a Gaussian? Gaussian PDF, okay, so the random variable is Gaussian if the distribution is Gaussian. So what is a Gaussian? Now the Gaussian PDF has a bell shape, so it's, you know, okay. So it's a function normalized to 1, which is centered into mu x, which is the mean. And we have one parameter which is sigma, and this sigma x is shaping the aperture of the bell. Okay, so it's like a bell. You know, if sigma is small, the bell is very narrow. If sigma is big, the bell is very broad. Anyhow, the area should be 1. Okay, so that one, you know, should be 1. Now in formula I say that the probability density function of Px is Gaussian when, you know, is indicated by a certain Gx, and this one depends on the mean, this mu x and this sigma x. Now it's easy to be verified that mu x is the mean value, so it's the moment of power 1, and sigma x is a central moment of power 2. Which is called variance. So sigma x is the variance and mu x is the mean. Okay. So when I indicate the Gaussian, I indicate by gx, and then, you know, mu x and sigma x. In formula, I can describe which is the exponential dependent. Okay, it has a bell shape. Now, what about the joint? Now the joint PDF, that means that I have two functions. So the joint PDF is Px and y. That depends on x and y, which are two variables. And, you know, this is by the formula. So I have 1 divided by blah blah, which is a normalization factor. Then it's exponential. So in the exponential I have 1 divided by 2 times 1 minus rho squared. And then I have different terms. So I have x minus mu x squared. I have x minus mu x has y minus mu y, and y minus mu y squared. Now you might recognize that this is a quadratic form. So this has a quadratic dependency. Now, so if there is x sigma x squared, okay, we will see what is that in a minute, sigma y squared, and then we have this rho. Now, this rho is called correlation coefficient. This rho is the expectation between the central expectation between x and y normalized with respect to sigma x and sigma y. This correlation coefficient is a number that is limited between 1 and minus 1. Okay. Now, if this correlation coefficient is equal to 1, that means that x and y are perfectly correlated. If it is equal to minus 1, that means that x and y are anti-correlated. Okay? So, what is perfectly correlated? What is anti-correlated? Okay? If I move on the opposite. Okay? Now, if rho is equal to 0, that means that they are uncorrelated. Okay? Now, for the special case of Gaussian, if a rho is equal to 0 and they are uncorrelated, they are also statistically independent. And let's see. So if rho is equal to 0, which means, if two random variables are uncorrelated, okay, which means, that they are uncorrelated. Now, they are, in this case, they are also statistically independent. Let's take the formula. Now we have a p x, y. Then we have an exponential part, the normalization part, and we have exponential. Now we have the first term, which is minus 1 divided by 2. Then I have, so I have x minus mod x squared divided by sigma x minus 1 divided by 2 y minus mu y divided by sigma y. But since exponential x a plus b is equal to x a times x b, okay, for this reason I can write this formula in this way. This one is equal to blah blah blah, so the scaling factor exponential of minus 1 half x minus mu x, and the other is exponential for the same argument. So if I go on the line above, that is exactly PDF of x and PDF of y. So we have a property very important that if I have two random variables and these two random variables are Gaussians, if these two random variables are uncorrelated, they are also statistically independent. Okay? So what is the shape? Okay? So the shape, of the 2D, the joint Gaussian PDF, okay, is this kind of bell shape. Huh? And for the picture here, for this picture, rho is equal to 0.6. Now, what is ruling this rho? So this rho, look at the axis, okay, this axis is x and the other axis is y. So you see, it is tilting. Okay, it's tilting. So rho is ruling, is deciding how to tilt this bell shape. Now, if sigma x is equal to sigma y, what's happened is that the bell is perfectly symmetric. Okay? If a sigma x is much different from sigma y, then the bell is narrow one direction, and so it's broader in the other direction. If a rho is changing, the bell is rotating. Okay? This is what you can easily check by yourself. By the way, I also inserted as a red line, okay, the conditional PDF just the slicing by cutting for y equals 0 and x equals 0. So this one is by cutting p, y, x equals 0. Okay. And similarly for the other. So this is just to give you the shape. Okay. So you can easily test yourself and see, how it is the shape. Now, in this picture, you can notice also in the bottom part some dots. Those dots are generated by randomly selecting one point to have a random distribution, to have a distribution that is Gaussian according to the probability density function that is indicated there. So what you notice there, you notice that, if you take a certain ellipsis, and we will calculate in a second, so if you take a certain ellipsis, most of the dots are contained inside the ellipsis. Okay? And so I might decide the size of the ellipsis according to the probability that the randomly chosen point belongs inside to the ellipsis or outside. And and it's very convenient to decide what is this degree of confidence, which means assuming that I randomly choose a point, if I take this area and I map this area, let's change the color of this one. I map this area, I calculate this volume. What is the volume? The volume now is telling the probability that one random value is contained inside in this area. Okay, because it's the volume, because it's the volume corresponding to the probability density function. So if I take this as area, I can calculate, given the area, I can calculate the corresponding probability. Okay? Which means, assuming that I randomly choose a point, what is the probability that this point belongs to this volume? This area. Okay? Now in 1D. In 1D, it's more straightforward. But this concept becomes very, very complex and multidimensional. But it's so important that it's better it's waste some time. So assume that our probability density function is this one, okay? This is Gaussian shape. So if I take this interval, okay, in this interval I can calculate by this area, and this area, which I don't know, it might be 0.9. Okay. Now this area is telling to me the probability that the randomly chosen point belongs to this interval. So the probability that x belongs to this interval, let's say A and B, okay, is equal to 90%. This is what it's telling. Okay? So that one is the two-dimensional version of this one, which is in 1D. Now, how to compute these ellipses? Now, the ellipses can be computed, and by the way, these ellipses is even more, more general, which is a volume. I didn't put it. Okay, no, I didn't put it. Too complicated. Okay. But there is a very easy, you can see in the book, okay? There is a very easy relationship between the probability and the corresponding, error ellipsis, okay, which is the ellipsis that contains all these points. Okay, there is a closed relationship. In a multidimensional case, so when the number of vectors is more than 2, this ellipsis is an hyperellipsis in the hyperspace. And it's very complex, let me say, to calculate that. Before I conclude, let me extend it to the multidimensional case and then we'll continue. Now, let's assume that, now I have a multidimensional probability. So what I'm going to say now is that, I want to describe the probability of a joint with respect to x1, x2, blah, blah, and xn. So now this one is a joint PDF with respect to the set. This second time, okay? Now, I don't want to keep x1, x2, x3, blah, blah, x25. I prefer to organize everything into a vector. Then rather than say it this way, I say that the joint PDF, so the joint probability, for the n-dimensional vector, so this n-dimensional vector is a vector of random variables. So the joint probability, which is the probability of the n-dimensional vector, is Gaussian. With now the mean is no more a mean, one number, is a vector of means. And correlation is no more a correlation, is a matrix of correlations. Now this matrix of correlation or variance is called the covariance matrix. Okay, in order to generalize. So this one is a covariance matrix, and this one is the mean. Even if it's you might say it's a mean because it's the mean of all the entries, but I simply say it's a mean, and that one is a covariance matrix, or in short, covariance. Okay. So the multidimensional probability density function in Gaussian case is indicated by this formula. Now, it's the square root of the determinant of 2 pi cxx. And cxx is the covariance matrix. Exponential of 1/2, okay, scaling factor, x minus mu x, which is x minus the mean, inverse of the covariance, x minus the mean. Now, you might recognize, I hope you did, but so you might recognize that this one, by the way, is still quadratic form. Now, so what are the covariance, or what are so the mean, the mean is simply computing the mean for every entry. So it's a vector of means. So it contains the mean with respect to x1, the mean with respect to x2, and so on. Okay. Now this is look at that. It's a row vector with a transpose, so it means it's a column vector. Okay. Now start getting practice with this short notation. Okay. So I don't write a vector in column, I write a vector in row and put a transpose. Okay, which means take a row, transpose means organize a column. Now cxx, what is a cxx? Now, look at that. What is a variance? Let me look at it here. What is the variance? The variance of a variable x, if it is a one variable, okay? Now the variable is a central moment of order 2. Which is, is the expectation of x minus mu 1 or mu x to the square. This is the variance. The covariance now, it's more rich because it has to contain the variance and the correlation factors. Now let's see what is into n equal 2. Because we saw n equal 2, so we need to recognize what we have seen before. Now, for the case n equal 2, the covariance matrix is equal to expectation of x1 square minus mu x1. This is the variance. So along the diagonal, and this is expectation x2 minus mu x2. Now, this one is the variance of x1, and this one is the variance of x2, which are indicated as a sigma. Okay? And what is the other? The other is expectation of x1, x2 minus mu x1 and mu x2. According to the definition of a correlation coefficient, this is a correlation coefficient multiplied by the square root of a variance, which is called the standard deviation. So it's a standard deviation on x1 and standard deviation on x2. So if rho is equal to 0, this covariance matrix becomes diagonal. Okay? Interesting. Now, in a general sense, the notation, look at that. When I indicate notation, is a way to indicate, the problem and the variable to solve. So in the notation, we say that x is a multivariate Gaussian with mean value mu x and covariance cxx. I indicate in this way. When I indicate this way, it means x is behaving as a distribution is normal with a mean that is mu x with the covariance cxx. Okay. And we stop here. We continue.